This meeting is being recorded.
In this chapter, we're going to be introduced to the concept of infrared spectroscopy and mass spectrometry later on. But the first part of chapter 14, we will review what's referred to as infrared spectroscopy and what we can gain from this type of analysis. So this slide here gives us this introduction to spectroscopy. And this term spectroscopy, IR specifically, can be abbreviated using these letters here for infrared, because it uses that type of electromagnetic radiation, infrared. So this type of spectroscopy will involve an interaction of matter and light, so that infrared light that we'll be referencing. And we know that light can be thought of as either a wave of energy or as a packet of energy, often referred to as a particle, and we call these particles photons. So this information should be somewhat of a review, including these relationships shown down here, that wavelength will be inversely proportional to energy. And if you recall the equation, E for energy equals hc, so we have Planck's constant times the speed of light over wavelength. This shows this inversely proportional relationship here. And then we have that energy in this equation here is directly proportional to frequency. So again, we see Planck's constant and then nu, the Greek symbol here, used to represent frequency. So we can utilize, again, that area in the electromagnetic spectrum, the infrared region, so this region here, and we can pass this type of energy through a sample and see how much of that is absorbed. So again, you should review the electromagnetic spectrum, not too deep in detail, but at least know what we're referencing here as far as the infrared region of energy. So there are many types of spectroscopy, some of which we will review in this semester. So we have NMR, abbreviated here, nuclear magnetic resonance spectroscopy. This utilizes radio wave frequencies, so the radio wave region of the electromagnetic spectrum, and this can tell us whether you're doing proton NMR or carbon NMR. It can tell you the specific arrangement of carbon and hydrogen atoms in a compound. Our focus for this chapter will be this IR, infrared spectroscopy. Of course, it uses those infrared wavelengths, and we can identify specifically functional groups that are present in a compound. So this is good to note. That functional groups can be identified. And then you've probably already experienced ultraviolet visible spectroscopy, which, as the name implies, uses both visible and ultraviolet light. And this we'll see in next semester in Orgo 2, that these conjugated pi systems can be identified through ultraviolet visible spectroscopy. So again, our main focus this chapter is the infrared. So when we talk about infrared spectroscopy and how matter can exhibit these particle-like properties, this is based on a quantum type of behavior. So at the quantum level, matter can exhibit both particle and wave-like properties as well, just like we note that light can. So on this molecular scale, when matter is taken down to individual molecules, we see this quantum behavior that's exhibited. So only certain energy, certain quanta of energy can make molecules rotate or vibrate. So those are going to be some of the responses that we see when electromagnetic radiation is applied to our sample. We're going to be focusing specifically on vibrations and bending. So when we talk about these vibrational energy levels that are quantized, when we have a covalent bond, a bond that as electrons being shared, we can add energy and cause a type of vibration depending on the amount of energy that is added. So in the infrared region, only certain covalent bonds will respond to the amount of energy that is being added. And we'll see that this type of vibrational energy levels, these are separated by gaps. So that's where we get this term quantized from, where there's only certain quantities of energy that will cause this type of vibrational excitation. So again, a photon of light strikes our molecule with that exact amount of energy. This light is absorbed, and then we see the result is that vibrational excitation. So again, we see this with covalent bonds and specifically covalent bonds that exhibit a dipole. So we'll continue with the specifics of bond stretching and bending that can be observed in infrared spectroscopy in our next section.